Welcome back. We are now starting section 4.3, logarithmic functions. Now, the definition of a logarithmic, and I want you to put the word function in quotes. The trigonometric functions, logarithmic functions, mean that you have a notation like f of x. There's going to be an argument at the end, sine of theta, logarithm of some number. It's denoted by log where there's a base b, and it's defined where if you have log of the base written there as a subscript below near the bottom of the g of some argument x equals y, that can be written in exponential form. Now I call this the swirly-do definition. If we circle the base of the logarithm, the b, the base of that logarithm is the same thing as the base of an exponent. So if you took b to the power of y, it should equal your argument x. In other words, we can rewrite that logarithm as base b to the exponent of y equals x. Now, in logarithms, we do have some restrictions. Our base has to be a positive number. If it's negative, then when you take it to a different exponent, it's just going to oscillate between a negative and a positive number. Also, our base cannot equal 1. Otherwise, no matter what the exponent is just going to give us 1. So might as well just write the number 1. And since our base has to be positive, that means that argument of x also has to be positive. So we've summed that up in the box below, logarithmic form and the exponential form. So when we're reading a logarithm, such as the one given in that first bullet point, that would be read log base b of x equals y. So x is our argument, but y is what a logarithm equals. So log base b of x equals or is the exponent. That is a huge concept with logarithms right here. Logarithms represent exponents. So that log is the exponent that you have to raise b to in order to equal x. And we're going to do some examples here in a minute. So since exponential and logarithmic functions are inverses of one another, that means that their domain and ranges are switched. So the logarithmic function has a domain from 0 to infinity, 0 not included, and a range from negative infinity to infinity. Now there's two specific types of logarithms. The first one is called the common logarithm or common log, and it has a base of 10 since we work in a base 10 number system. Tens, hundreds, thousands, 10,000s, and it's denoted by log with an x. Notice there's no base seen. We would just read that common log of x. The next one we call the natural log, and the natural logarithm has a base of e, Euler's constant, and it's denoted by ln of our argument, and we would just say take the natural log of x. So we could write it with a logarithm with a base e, but this is a shorthand. Now, I want to show you guys something on your calculators. So if you look on the left-hand side here of your calculators, you see the log and you see the ln, but look at the second function that's noted above each of those buttons. On top of the log or the common log button is 10 to the x. So that's even kind of a nice little cheat sheet on your calculator reminding you that if you don't see a base, that common log has a base of 10. Likewise, the natural log, the ln button here, has a second function, e to the x, to remind us the base of the natural log is e. Well, we're not going to be using our calculators just yet. We want to get used to what a logarithm represents first. So in this first example, we want to rewrite the exponential equation 2 cubed equals 8 as an equivalent logarithmic equation. So remember, if we start with log, the base of our logarithm is also the base of the exponent. So the base of our exponent is 2, so we're going to have log base 2. And remember, the logarithm represents the exponent. So I usually write the equal sign first. So 2 cubed equals our argument 8. So we have log base 2 of 8 equals 3. Again, you can kind of see where the sorely do comes from. So just always start with your base. So in part B, we want to rewrite the logarithmic equation log base 3 of 1/9 equals a -2. Base 3 is going to be the base of our exponent. So we have 3 to the power of -2 equals our argument, which is 1/9. And that's a true statement. Remember, negative exponents means reciprocal. And if we square 3, we get 9. So let's do several examples. And we want to evaluate each expression if possible. So there's a hint, some of these may not be possible. So log base 5 of 125. This is asking us 5 to what exponent would give us 125? Well, that would be 3, since 5 cubed equals 125. We have the logarithm base 4 equals 1 over 256. Sometimes it's helpful to rewrite that argument in terms of your base. For example, this log of base 4 is equivalent to 1 over 4 to the 4th power. If we didn't want to write it as a reciprocal, we can use our negative exponents, 4 to the -4. So this is asking us 4 to what exponent would give us 4 to the -4. So 4 to what exponent would give us 4 to the -4. When you rewrite it like that, it feels almost like Sesame Street logic, you know, this side must look like the other. So it has to be 4 to the power of -4 in order for it to equal 4 to the -4. Part C, notice we do not have a base that is seen. That means if it has the log that we are using a common log. The common log of 100 is asking us 10 to what exponent gives us 100? Well, that would be 2, since 10 squared equals 100. So that base there is an understood 10. Part D, here we have a natural log of 1. This is asking us e to what exponent equals 1. Because remember that base, even though we don't see it, is an understood e. So the natural logarithm has a base of e. So e to what exponent equals 1? Well, there's only one exponent that no matter what base we have, to this exponent, it always equals 1. And that is 0. So anytime you have a logarithm, regardless of the base, if it is a logarithm of 1, it will always equal 0. Here we have another common log. So this one is asking us base of 10 to what exponent would give us a -10. Is there one? Even if we took it to a negative exponent, that wouldn't change it to a negative number. It would just take the reciprocal. Like 10 to the -1 is 1/10. Even 10 to the 0 power is a +1. So remember at the beginning, we said that that argument, that x value has to be positive. So this one does not exist. And the reason is since -10 is not in the domain. What about the natural log of 0? That's asking us for the exponent that if we took e to that exponent, it would give us 0. Well, even e to the 0 power gives us 1. So whether it's a negative exponent or a positive exponent, this one also does not exist because remember our argument has to be greater than 0, not greater than or equal to. Because remember our domain was greater than 0, not greater than or equal to. Now let's take a look at G. Okay, so this is going to take a little bit of thinking. We have 10 as a base, but it's a base of an exponent. The logarithm is in the exponent position. So before we simplify this, let's take a look at what log of 7 is saying. So that's an understood base 10. What this equals is 10 to that exponent should give us 7, whatever that exponent is. Well, we don't know what that is. So what we can do is define it as, let's say, an n. Log base 10 of 7, or the common log of 7, equals some number n. That's the exponent. Well, guess what? We are taking 10 to that exponent. We can substitute it in for that exponent minus 1. Well, remember what that logarithm means. 10 to the power of n equals 7. So we can use substitution. So that equals 7 minus 1, which gives us 6. So if you have a base of 10, let's say, or any base, taken to a logarithm of the same base, it's going to equal your argument. Matter of fact, let's write that out to the side. We'll get into these properties a lot more later, but it's saying if you have a number, let's call it p, and it's taken to the logarithm base p of some argument, remember that logarithm represents the exponent that would give you x. Well, p is being taken now to that exponent, so it would equal just x. This is the same issue. We have a natural log, therefore we have an understood base e. So e to what exponent would give us e to the negative 3.5, negative 3.5, which gives us a 1.5. So again, just a little scrap work down here. That means e to what exponent would give us e to the negative 3.5. Base of the argument equals the base of the logarithm. So these two here should be the same. So that's why it just equals negative 3.5. So we get 1.5. So you're going to practice some of these in your homework if you can get them in terms of the base, and if you need to rewrite the base for like the common log or the natural log, write in that 10 or the e, go for it. Just notice there an h. Some people think that e is already in the base, but it is not. If you see that ln, that base is never written. So if it helps you to write it in at first just to see it, to know that those are two different e's there. I hope that helps. If you have any questions, you know where to find me. Talk to you soon. Bye.